for attending my talk. So I'm going to talk about some principles behind randomized algorithms for convex optimization, which are variance reduced, which means that the variance, the error due to randomness, will automatically decrease over the iterations to eventually vanish, so that the algorithm will converge to the exact solution. Also, it is randomized in the first place, which makes the iterations cheaper and even much cheaper than the deterministic counterparts. So this is joint work with Peter Richterik, the head of the optimization machine learning team in KAUST in Saudi Arabia. So this is the setting. We want to solve a convex optimization problem, which is written here. I don't know if you can see my mouse, but it's written at the top. So we want to minimize the sum of functions. We have a sum of functions fm, which are supposed to be smooth. We have an arbitrary number, capital M, of such functions. So each function is L smooth, which means that the gradient is Lipschitz continuous with the constant L. And we have possibly an additional function R, like a regularizer, which is not supposed to be smooth, and we will make use of its proximity operator, whose definition is recorded here. So we set for conveniency f as the average of the functions fm. So now we want to minimize the sum of two functions, f and r. F is smooth, and we will make use of its gradients. The gradient of the sum of functions is the sum of their gradients. So in this talk, we assume for simplicity that f, this average function f, is strongly convex. So this is a restricted setting, but it already allows to understand the mechanisms behind the theory of developing variance-reduced algorithm, and then we can extend to the merely convex and even non-convex settings. But in this talk, I focus on the strongly convex case in which we will derive linear convergence theorems. So the function f is supposed to be mu strongly convex, or this mu constant, which is supposed to be positive. So here it's important to note that the functions fm individually are not necessarily strongly convex. Only the average is supposed to be strongly convex, which is a weaker assumption than what we can find sometimes in the literature of SGD. So the convergence speed, so we will have a linear convergence with a rate that depends on the conditioning, which is mu, the strong convexity constant, divided by L, the smoothness constant. So this factor depends on, so it's between 0 and 1, and the smaller, the worse. So the convergence will be slow if mu over L is very close to 0. So the baseline algorithm to minimize the sum of two functions is the proximal gradient descent algorithm, also called forward-backward algorithm. So mathematically, it is written like this, quite simple. So we first perform a gradient descent step. So we take xk, our current estimate at iteration number k of the solution. We subtract the gradient of the smooth function f, so which is the average of the functions fm. So we have the average of the gradient of fm evaluated at xk. We have a step size gamma, so this is a gradient descent step. And then we apply the proximate operator of the regularizer, if there is one, with the same step size gamma. And we get xk plus 1, the next estimate at iteration k plus 1 of the solution. All right. So we want to design a randomized version of this algorithm. So the theory is now well established. So if gamma is chosen in this interval, we have linear convergence, which means that we have a contraction. So the distance between xk, the current estimate of the solution, and x star, which exists and is unique. It's the solution of the problem because we have supposed that the problem is strongly convex. So the solution exists and is unique. So this distance is decreases and is shrunk by a constant factor, which is 1 minus gamma. Gamma is the step size times mu, the strong convexity constant. All right. So what's the challenge? What's the difficulty here with this proximal gradient descent algorithm? So in the non-distributed setting or sequential one, which is when we run the algorithm on a single machine, this capital M, the number of functions, can be very large. And this is the bottleneck here, because in training machine learning experiments, M is typically the number of training samples in the data sets that we want to use for training a neural net or to find the model. And because this number of capital M is very large, here when we implement the algorithm, this sum here is a loop. So we have to compute all these gradient of Fm for M very large at every iteration. Okay, so we would have a loop over M, and we would need to compute all these gradients that can be costly because the model lives in R D here. D is a dimension. If X is a vector, would be the vector of the weights of neural net or the number of parameters in the model that we want to find. So the computation cost of every iteration scales like D, the dimension of the vectors, times M, the number of functions. So D times M is possibly huge, and we don't want to run computation which scale like D times M at every iteration of an algorithm, because the number of iterations to converge can be of order several thousands. So if each single iteration takes hours or even days, it's too costly. That's why we will call for randomness, because this deterministic baseline algorithm is too costly typically for large training settings where capital M, the number of functions, is large, and D possibly also large. So we don't want, we don't want to scan the entire data set. This would be, for instance, a very large base of images, all images in the internet. And we want to make use of all these images to train a model finding cats in images, for instance. We don't want to scan all the images at every iteration of the algorithm. So this would be the challenge in the non-distributed setting. Now in the distributed setting, the challenge is slightly different, but we will see that the solution is actually by means of using randomness. We will address these different challenges in the same unified way. So the distributed setting is the following. We have a master node communicating with the number capital M of parallel nodes or workers. So, and these workers can have heterogeneous properties up to the extreme, which is the so-called federated learning paradigm, in which we private data stored on it, and communicating back and forth with the distant server, which can be some virtual entity in the cloud. And they are all collaboratively involved in solving training tasks. So for instance, learning, training a text prediction app. So, you know, in Google, when you type something, it predicts what is likely to come. So if I type an A, there is the word Amazon here in my computer, which appears, which is suggested. So this could be an example of training a huge model of text prediction in this distant service, which is Google, by communicating back and forth based on the daily what is done by all the users using Google in the world. it could be an example of federated learning. So all the users have to are involved in this collaborative process of learning the text prediction model used by Google. Or we could imagine healthcare centers, for instance, with the private data stored on each of them, so like the X-rays of the patients, and they're all involved in a joint process of learning some good procedure protocol to be used at the national level, for instance. So they have to communicate back and forth information, but they don't want to send the private data. So there are privacy concerns here. But the main bottleneck is this communication between the users or workers and the distant server. So if we look at the proximal gradient descent in a proximal gradient descent algorithm in a distributed setting now, it proceeds like this. So the master sends the current estimate xk to all workers. Then each worker computes the gradient of its own function, modeling its own individual cost associated with this model. So each user computes the gradient, and then all the users send these gradients to the master, which just averages them. So it aggregates all these gradient vectors, computes the average, then performs the gradient descent step, and applies the proximity operator. And the main challenge here in this distributed setting is the cost of communication. Okay, so this is sending these vectors, which are possibly large. So these are vectors of dimension d to the master is possibly very slow and costly. Okay, because these are smartphones, so the users have to use their data budget to solve these vectors to the master, and doing so at every iteration of a procedure for hundreds or thousands of times would be very costly in terms of communication budget. So this is slow and costly. This is the communication cost that we want to decrease in this distributed setting. The number m of clients is not the bottleneck in this case. It can be very large. And if m, the number of workers, is very large, it will even help to solve the problem actually in this distributed setting. So m is not the bottleneck. This is d, the dimension of the vectors actually here in this distributed setting. So in both cases, in non-distributed and distributed setting, we want to we have difficulties, and we want to do stochastic gradient descent instead of gradient descent, which means we have the same algorithm, but here instead of the true gradient is here, we want to make use of an estimate of the gradient, which I call GMK, so at iteration number k for worker or function number m. We have this estimate, this approximation of the true gradient of fm evaluated at xk. That will be used in the gradient descent step. That will be typically much cheaper to compute or to communicate than the true gradient. That's the idea. And this talk we will make use of a random estimate of the gradient, which will be even assumed to be unbiased. So we have a random estimate. GMK is a random estimate of the gradient, and its expectation is exactly the true gradient. So this is what it means to be unbiased. In this talk, we will assume unbiased stochastic gradient estimates, but we could also extend the theory to the use of biased estimates, which can have some advantages. And I refer you to my recent paper on this topic, where we extend the theory from unbiased to arbitrary, even biased estimates. In this talk, we focus on the strongly convex setting with unbiased estimates of the gradient. So let's see some examples of stochastic gradient estimates which can be used. So the first one is probabilistic activation. So the stochastic gradient is equal to the true gradient with some probability p and k, which can be very small, and to 0 otherwise. In that case, it means that with some small probability, the stochastic gradient will be equal to the true gradient. So we have to compute the true gradient in that case, but only with small probability. And otherwise, the gradient will be 0, so there is no cost in computing the stochastic gradient estimate. So with large probabilities, this estimate will be 0. So that's the way we will reduce the computation cost in that case, because we need to compute the gradient only with a small probability in this example. And 0 is clearly a bad, very naive estimate of the gradient, but we will see how through variance reduction technique, it will actually be a good idea to do so. All right, so in this, so we have a scaling here by 1 over the probability to make it unbiased. So we can check that this estimate is actually unbiased when we take the expectation. All right, this is the first example. The second example is called the mini batch gradient descent or sampling. So we don't evaluate all the gradient, but only a few of them. So we first choose which indexes. So we first pick a random subset of omega k of all the indexes from 1 to m, because you have capital M functions, but we want only to select a few of them, even though only one, for instance. So n is the size of this mini batch or sampling set. For instance, if n equals 1, we just take one of the index to the uniformly at random, and we evaluate the gradient only for this mini batch, only for these selected functions, and the estimate is 0 otherwise. It's similar to probabilistic activation, except that now the process is dependent. We first select the indexes and evaluate the gradient for these selected indexes. This was the second example of a stochastic gradient estimate. The third example is compression. So this would be for the typically for the distributed setting, where d, the size of the vectors, is a bottleneck. So because we have vectors, big vectors, so we will actually communicate not the d coordinates, but only a few of them. So we so there is this compressor which is called the round S or 1k. So S is the number of elements that we choose out of D, that are chosen uniformly at random, and we communicate only these coordinates, these D coordinates, S coordinates, sorry, instead of D. So S is small, D is large. So this way we will decrease the communication cost by sending to the master or server only D values instead, S values, sorry, instead of D. Next example would be quantization. So these values of the vectors that we communicate are real numbers. So typically they're represented using a certain number of bits, like 32 bits for each double precision float. So we can decrease this cost using randomized estimates. For instance, if we want to send the real number 0.2, we would send 0 with probability 4 over 5 and 1 with probability 1 over 5. So we can check this non-biased estimate, random estimate of the number, and it will take less bits to send this binary approximation instead of the full floating point number with many digits. So some aspects of the trade-off between number of bits and error of investigated in this paper with my colleagues, which is indicated here. So we can, so these were simple examples, but we can figure out more complicated examples of stochastic gradients. For instance, this one based on permutation by some people in our group consists in choosing the indexes, so compressing the vectors by choosing some random indexes, some random coordinates that we will send to the communicate to the server, but in such a way that they arrange together to form a permutation, and this has some favorable properties in comparison with just selecting the coordinates at random independently for each user. All right. So these were some examples of stochastic gradients that we can use, and this will decrease either the computation or the communication cost of evaluating or communicating computing or evaluating the gradient of all these capital M functions at every iteration of the algorithm. Okay, but this is not, so having unbiasedness is not sufficient. We want more because we want the algorithm to actually converge, to eventually converge as k tends to infinity to the exact solution of the problem, not an approximation, which would be the case if the randomness was constant, that the algorithm would always oscillate even close to the solution, would always oscillate in the neighborhood. This is not what we want. We want xk to converge exactly to x star, which means that we want the randomness to also decrease. Okay, so we want xk to converge to x star exactly. So this implies that the randomness, so the expectation of the error between the true gradient and the stochastic gradient should tend to 0 as well. Okay, so we will see how to enforce this property, that the error between the stochastic gradient and the true gradient vanishes. So to do so, we will not randomize the gradient, as I showed before, but actually the difference between the gradient and another variable we can call a control variate, denoted by h here. So that this difference, this error tends to 0 along with the iteration. So for this, the control variate h and k should converge, just like the true gradient. It should converge to the gradient at the solution. Okay, along with the iteration, it should converge to gradient of fm at x star. X star is the solution to the problem. So, and then the algorithm will look like this. So the stochastic estimate, the stochastic gradient estimate, GMK, will not just be, so it is a randomized, unbiased estimate of the gradient, but it looks more in details. It will look like this. So we will apply some randomization operator. So it's denoted by C because of compression in the distributed setting. It could be a compressor. But more generally, it is a randomization operator that is applied to this difference between the gradient and the control variable. Okay, so this is this quantity that is randomized, and that tends to 0. And we add back the control variate to make it unbiased, because when we take the expectation, so the expectation here is equal to this. When we add back HMK, so the expectation is equal to the true gradient, which is exactly what it means for GMK to be an unbiased estimate of the true gradient here. Okay, so this CMK is a randomization operator. We have seen some examples before, like probabilistic activation, for instance, where we would compute this quantity, this vector here with a small probability, or put 0 also. Okay, so it does. So this is an abstract randomization operator. It does not mean that we necessarily computationally evaluate this first and then give it as an argument to an operator CMK. In the probabilistic setting, for instance, we would evaluate the argument only if it is present in the output of the stochastic estimate. Otherwise, we don't compute the gradient. Okay, so if we choose with small, we flip a coin. If we decide that we don't, that the output of CMK is 0, then we don't evaluate the gradient in that case. Okay, but mathematically it is written as if we the difference between the gradient and the control variate would be the argument of this randomization operator, but I've written that it is an abstract operator to denote the fact that it's actually just a notation, mathematical notation, to denote the fact that we have this randomized estimate of this difference here. All right, so it has to satisfy two properties. It should be first unbiased. Okay, so the expectation of randomized version of vector V should be V. V is the difference here, typically. And for any V. And the errors, the randomization errors, so the expectation of the square norm between the difference of square error between the randomized version of V or compressed version of V, this is compression, and V, should be bounded by the square norm of V times a parameter which is omega. Yeah, which gain, I call it the gain of. So if V has a small norm, the error should be small. If V is close to 0, this error should be small. If V is large, we don't care, the error can be large. So that's the idea of variance-reduced algorithms, because this quantity will tend to 0. So if we are close to the solution, the randomness will be small. So randomization error will be small if we're close to the solution, but at the beginning of the algorithm, where the distance here to the solution is large, we can allow for large random errors. So this will make the algorithm progress rapidly at the beginning, and when we are close to the solution, then it will eventually converge to the exact solution as we design. So these two properties are satisfied by all the examples before. We can check that this is true. For instance, with the probabilistic compressor, we can check that it is unbiased. So C of V is equal to V scaled by 1 over P with probability P, and 0 otherwise. So we see now why there is a 0 here and not anything else. 0 plays a particular role, because if V is 0, then there is no error. Okay, so C of V is C of 0 is 0. Okay, so if the estimation error between the gradient and the control variety is 0, which is the case at convergence, then there is no randomization error. And we can check that it satisfies this conic error property, so with omega equals to 1 over P minus 1. So if P is equal to 1, then there is no error. Okay, so the stochastic gradient is equal to the gradient exactly. So P equals 1 means that omega equals 0. Omega is the error, so the controls the error. If omega is small, there is low randomness. And if P is small, then this omega can be very large, the amount of randomness. But we'll see that the algorithm will converge whatever omega. And we can note that the different randomization operators, which are applied to all these vectors, all these differences M, they can be dependent. So this is a joint random process. Okay, and we have seen the example of mini batch sampling, in which this is the case. The operators are mathematically dependent because we first select a subset of not coordinates, but functions M, for which we will compute the gradient, and then we evaluate the gradient for the selected ones. So this is, in that case, a dependent joint random process. Okay, so now using this shifted gradient estimate, let's see how the algorithm look like. So this is the first algorithm. We will elaborate on it further on later. So the randomized version of proximal gradient descent. It looks like this at every iteration. K is the iteration index. For all functions, we mathematically, for all functions, there is a loop. We evaluate this randomized version of the difference between the true gradient and its the control variate, so an estimate. We update the control variate using lambda is the parameter times this is difference, which has just been computed. Then D is the average of all these differences dm. And we perform the stochastic gradient descent step. So now the estimate of the gradient is hk plus dk plus 1. Yes, so this quantity here is an estimate of the gradient of f. F is the average of all the fm. And we apply the proximity operator, and we update the average control variate h. H is the average of the HMK. So it's updated in the same way as all the HMK. All right, so we have now an algorithm, which is a proximal stochastic gradient algorithm, and which we will prove to converge to the exact solution of the problem. So let's to explain what it means. Let's look at it in the distributed setting. So the beginning is the same. The master sends or broadcasts xk, the current estimate of the model, to all the parallel workers. They evaluate the gradients in parallel. Then they evaluate this difference by applying the difference between, so each worker has a control variate, which is maintained locally. So it randomizes, worker randomizes this difference between the gradient that has just been computed in the control variate. So this yield a difference vector dk, k plus 1. And these are these vectors which are sent to the master. Okay, so the vectors that are sent to the master are now compressed version of the differences between the two gradient and the control variate. Okay, so in the randomization or compression operators, they can be designed in such a way that it takes less bits to send than the true full vector, which will be in ORD. So if we have selected a few coordinates of the vectors, for instance, it would just take S coordinates to send instead of D. If we have quantized these real numbers, it takes less bits than 32 bits times the number of floats, and so on and so forth. Okay, so here we send a compressed or randomized version of these differences to the master. Then just take the average, and so it forms this.
5 more minutes.
Sorry?
I have 5 more minutes.
Okay, 5 more minutes. Okay, good.
Right.
I have my timer. Good, thank you. So it forms a gradient. The estimate of the gradient is hk. Okay, the control variate, which is available at the master. It adds up this average of the difference which has just been received. So this way it forms an average of the estimates of the individual gradients here, which is actually an estimate of the average gradient of the smooth function. Okay, and it uses this stochastic gradient to perform the gradient descent step and applies the proximity operator. So this is how the algorithm works in the distributed setting. So now there are two questions. The first is how to choose this lambda parameter, which is the parameter which controls the update of the control variate. So it's the variance reduction mechanism. The speed at which it evolves is controlled by lambda. And the theory tells us that it's quite simple, and we just set it as 1 over omega plus 1, where omega is this gain of this factor controlling the amount of randomness. So if there is no randomness, omega is 0, lambda is equal to 1, and we recover exactly gradient descent. And gamma is the step size using gradient descent or learning parameter, and we will see later on how it is chosen, depending on the strong convexity, so conditioning, and also the factor omega. So to decide on to choose the gamma and find the convergence rate, we actually need some more quantity, some additional quantities, not just omega, but an additional one, which is the average gain. average relative variance, omega average. And there is also an offset, zeta, which appears here. But we have to analyze how the randomness behaves after aggregation, after averaging the random estimate of the individual gradients, individual stochastic gradients. So we have these individual stochastic gradients obtained by randomization of all of them, but then they're averaged. So what matters in the algorithm is how the amount of randomness that remains after we have averaged this stochastic estimates of the vectors. And this is controlled by this factor omega average. So it is the expectation of the squared error between the average of the differences between the randomized vectors and the true vectors. So omega average is always less than or equal to omega, because this formula is satisfied if we plug omega instead of omega average. But the goal is to have a value which is much smaller than omega. So in favorable cases, omega average will scale like actually omega divided by n. And this is the case if the randomization operators are independent. So that would be the case with round K, round S, where we select a small subset of the coordinates that will be sent to the master for every vector. In parallel, we select random coordinates, and if these selection processes are independent, then when we average the vectors, we know that the variance of independent random variables is the sum of their variances. So when we average, there is a 1/m factor which appears, and which is very good, because the higher the number of, the larger the number of workers, so capital M, the smaller the randomization error. Because so the convergence rate will depend on omega average, not omega. This is the main point. Okay, so for sampling, for instance, we can derive the exact parameters which are here. So we see that omega is equal to this quantity. So if n, the mini batch size is equal to 1, omega is m minus 1, which can be large, but omega average is equal to m minus 1 over 1, m minus 1 is equal to 1. Okay, so for sampling with only one sample at every iteration, then this value omega average is equal to 1, whatever m. And so now we can go to the next step, which is making the algorithm a bit more complex. So instead of using the same randomization process to compute the stochastic gradient and to update the control variates, we use two different processes. So we have randomization operator CMK, which are used to make these differences, which are used in the stochastic gradient descent step. And we have also a different mechanism to update the control variates using another set of operators U. So this is here the second algorithm, and we can design examples. I propose a new algorithm called Elvira in the paper, which looks a bit like loopless SVRG, if you're familiar with SVRG. So there is a different mechanism for updating. There is a probabilistic mechanism for updating the control variate, and a sampling mechanism for computing the stochastic gradient. And we can even make the algorithm even more complicated. This yield now the general algorithm, which is called MURANA, which is proposed in the paper from MURANA for kind of, it's multi-randomized algorithm, which looks like this. So we have an additional third mechanism to do model compression, to compress the difference or randomized difference between xk and xk plus 1. So this is to compress this broadcast, this first communication step in the distributed setting. All right, so I'm almost finished. Let's just comment on the convergence theorem. So we have linear convergence if gamma, the step size, is chosen in this range, which is controlled by omega average, this relative variance of the randomness. By choosing gamma in this range, then we obtain linear convergence, and there are two factors. there is a 2 gamma mu factor, which appears here, and a constant factor, which depends on the randomness of updating the control variables here. So we have the maximum of 2 mechanisms, which yields a complexity, which can be written like this. So typically, the accuracy, the iteration complexity to achieve epsilon accuracy is given here. So it depends on the conditioning multiplied by 1 plus omega average. But omega average is typically small, plus some constants that can be large, but that does not depend on the conditioning. So typically, the computation complexity can be reduced from the classical gradient descent to m times conditioning to conditioning plus m. So this is, we transform the product of the conditioning times the number of functions to just their sum. So since the non-distributed setting and the distributed setting, the communication complexity becomes d, the size of the vector, times the conditioning to conditioning plus the dimension, which is much better for large dimensions. So to conclude, we prove the linear convergence of the very general algorithm MURANA that recovers many known algorithms like Saga, SVRG, Diana. We prove linear convergence, and we have a rate with an explicit form. And there are, for future work, there are many open questions like how to do how to plug an acceleration in the nested of sense, how to use biased estimates in this generic algorithm, and how to extend the theory to the convex and non-convex case, and even to algorithm for non-smooth optimization.